Welcome to AS level physics class. Today a topic is taken from Unit 1 Mechanics and Material, and today's topic is fluid dynamics. So in this fluid dynamics, what exactly you need to know? You need to know about fluids, the different characteristics of fluids, and also the fluid forces. In addition to these fluid forces, how they affect the motion of object in a fluid based on Archimedes principle, Stokes law, terminal velocity, and even all different types of fluid flow. And you would get to see the practical applications of this fluid dynamics also in this session. So let's move on to the session. I am Majida, representing Center for Higher Secondary Education. So to start with the fluid dynamics, what are fluids? Fluids are substances that can easily flow. So as you all know, fluids, it includes both gases and liquids, because they can easily flow and take the shape of the container where they are enclosed. In order to understand this fluid characteristics, one of the important factors that you should know at this point is the density. Density is defined as mass per unit volume. So when you say, it's a basic definition of course, mass per unit volume, so it says a unit is kilogram per meter cube. But why are we stressing this density in fluid dynamics? Here you get to question something like this. If density of fluid is some value, what does it mean? For example, density of water is 1000 kilogram per meter cube. What does it mean? It means 1 meter cube water has a mass of 1000 kilogram. So you should be very clear what is the significance of the value density. But whenever you are asked to find the density, you can actually find the density in kilogram per meter cube, that's a SI unit. You must be wondering, what's the force that keeps ships floating and the hot air balloon remains in the air? Do you know what's the answer? So it is some fluid force that is keeping it in that state. But what exactly is that fluid? For any given object, there is a downward force, what we call the gravitational force. The weight acts vertically downwards from center of gravity. So if it is floating or balanced, means the forces acting on it must be balanced. So in order to balance this weight, there should be an upward force that is offered by the fluid, and that particular force is responsible for the object to remain at rest or balance, we can say. So you should be familiar with the important fluid forces. The first important fluid force is upthrust. What is this upthrust? Whenever an object is submerged or immersed in a fluid, the fluid exerts an upward force on the object. It's because when an object is actually immersed in a fluid, it displaces its own volume of the fluid. And that displaced fluid gives an additional force on an object. The upthrust always acts on the object in the upward direction. This particular upthrust force is equal to the weight of the fluid displaced according to Archimedes principle. So what is this Archimedes principle? Archimedes principle states that whenever an object is partly or fully immersed in a fluid, the upthrust experience is equal to the weight of the fluid displaced. So when you talk about upthrust is equal to weight of the fluid displaced, we can say the weight. How do we express this weight? If you look at here, I have given that actually rho Vg. How exactly this formula arises? This weight is actually mass of the fluid displaced into G. Mass of fluid displaced can be written in terms of density. So that is how this formula arises, rho V into G. You must be wondering what must be the unit of this upthrust. It is thrust, it is a force. So, the unit is Newton. So, rho f v into g. But when you are asked to calculate upthrust, sometimes the students are confused whether to go with the density of the object or density of the fluid. Remember, always it is the density of the fluid. So, Archimedes' principle clearly states that whenever an object is partly or fully immersed in a fluid, the upthrust experienced is exactly equal to the weight of the fluid displaced. So, you can use this equation to calculate upthrust in any of your calculations. The second type of fluid force that comes into picture here is viscous drag, or we can say that actually just the drag force. When will this drag force act on an object? If an object starts to move in a fluid, the fluid offers a resistive force on an object. That resistive force only we call it as viscous drag. Unlike upthrust, upthrust always acts in the upward direction, whereas viscous drag always acts in the opposite direction to the motion of the object. If the object is moving downwards, the viscous drag will be acting upwards. But if the object is moving upwards, the drag force will be acting downwards, always opposite to the direction of motion. But this viscous drag depends on the speed. More the speed, more would be the viscous drag. And let us see the effects of these forces on in real life situations. See, how does a hot air balloon go up and down dancing in the air? Sometimes actually you could see the hot air balloon almost it remains still. Sometimes it goes up, sometimes it goes down. So, how do you explain this practical situation with the help of fluid forces? If you look at the fluid forces, we have learned now the three important forces: weight, upthrust and viscous drag. How these forces act on the object to keep it balanced. When the object is actually just still or floats, we can say weight is equal to upthrust. But if the hot air balloon is descending downwards, it is clear that the upthrust plus viscous drag and the weight actually is not balanced, and the downward force is greater than upward force. Now, it is very clear if the hot air balloon is rising up, so the total upward force would be greater than downward force for it to move up. So, the magnitude of these forces changes according to the motion of the object. But the effects of upthrust. What happens if the upthrust is smaller than weight? If the upthrust is smaller than weight, the object sinks. In fluid dynamics, you should know very clearly if the upthrust is less than weight, what exactly happens? And if upthrust is equal to weight, what happens? But if upthrust is greater than weight, what happens? These are the three important terminologies, conditions in which you should know to actually explain what exactly happens to the object. So, it is very clear upthrust is smaller than its weight means object will sink. Whereas, if the upthrust is just equal to its weight, then the object will be able to stay anywhere in the fluid, or you can say it floats. If the upthrust is larger than the object's weight, the object will start to move upwards. But at one point what happens means the forces acting on it are balanced and the object starts floating. Now, let us see this viscous drag. We said about the viscous drag. How exactly the viscous drag arises in a fluid? It is due to the intrinsic property of the fluid, what we call the viscosity of the fluid. So, what is this viscosity? It is it's the intrinsic property of the fluid, the factor or the quantity which is the measure of the stickiness of the fluid. More the stickiness, more would be the viscous force or viscosity. The coefficient of viscosity is the ideal quantity here, which gives the measure of viscosity. which is represented by the symbol eta. So you are familiar with this particular symbol eta for coefficient of viscosity. It has the unit Pascal second, and you will know actually why is it exactly Pascal second, or it can be even expressed as Newton per meter square in the second, in other words Newton second per meter square. You will get to know why the unit is this. Before moving on to those units, the viscosity or coefficient of viscosity, how does it affect the viscous drag? Some liquids are more stickier than others. If I take an example of honey and water, honey is more viscous than water. So if an object is actually allowed to move through a tall jar of honey, it actually moves slower when compared to the object which is dropped through a jar of water. Why? There is a difference in speed. Both are accelerating downwards due to gravity. But the fluid or the liquid here offers a resistive force. The honey has higher coefficient of viscosity than water. So it offers more resistive force than water. So in the case of honey or the liquid or the fluid which has higher coefficient of viscosity, the resistive force experienced by the object will be more. So you can see from here, the viscous drag is larger while moving in a fluid with a larger coefficient of viscosity. So it's a very important question actually, open response question, you can expect this particular point. So you should know to compare the viscous drag experienced by the same object when it is descending through the fluids of different coefficient of viscosity. So hope it is very clear now about the effect of coefficient of viscosity or the viscous effects, how does it affect the drag force. But this viscosity or coefficient of viscosity is actually constant property of a fluid at a given temperature. But if temperature changes, the coefficient of viscosity also changes. In the case of liquids, if the temperature increases, coefficient of viscosity decreases. Whereas in gases, as we increase the temperature, coefficient of viscosity also increases. So at this point, you could get an application type question. If the temperature of the fluid is increased, how does it affect the viscous drag experienced by the object? So you should know to explain in relation to how the coefficient of viscosity changes, thereby the viscous drag force. For example, in the case of liquid, temperature of the liquid is increased. So what will happen to the coefficient of viscosity? Coefficient of viscosity decreases. So what do you expect the viscous drag experienced by the object in a hotter liquid? It will be less compared to the colder liquid. So like that, you should know to explain and link the concepts in explanation and extended writing questions. This particular coefficient of viscosity is defined with the help of the Stokes' law statement. What exactly is the Stokes' law? The Stokes' law is mainly targeting on small spherical object. So it gives the clear-cut idea about the viscous drag experienced by small spherical objects when it descends through a fluid. If you consider an object of radius r, which is descending through a fluid of coefficient of viscosity eta and at speed v, the viscous drag experienced by this particular object, you can see as from the equation. How this equation arises is, the viscous drag experienced by the object is actually directly proportional to coefficient of viscosity, the radius of the object, and the speed at which it moves through the fluid. To remove this constant proportionality, we introduce a constant, that constant only 6 pi eta r. So this equation actually defines, or if you want to define coefficient of viscosity, you can make use of this formula, write this formula and clearly explain the meaning of all the symbols. In this equation, F is the viscous drag, eta is coefficient of viscosity, r is radius, and v is the speed of the moving object, you can see. So, as per this equation, you can easily come to a conclusion how the unit of viscosity is Pascal second. If you are asked to show that the unit of viscosity of the fluid or coefficient of viscosity is Pascal second, you can make use of this equation, make eta as a subject, and it will have the unit of the force per radius and the velocity. So, there you will be able to show that it is Pascal second. So, it is otherwise Newton per meter square into second, that can also be expressed with this unit. But there are two important conditions for Stokes' law to be valid. The Stokes' law is valid only for small spheres, and the fluid flow must be a regular, smooth, or we can say a laminar flow. Towards the end of today's session, you will be learning about the different types of fluids. Until then, we will just move on to the next section, how this Stokes' law is actually helpful in finding the coefficient of viscosity. So, here the very important concept actually, how this terminal velocity arises. Now, the forces acting on the object in a fluid or keeps on changing. For example, if I am dropping an object through a viscous fluid, the moment we are dropping, the only force that is acting on the object is the gravitational force or the weight alone. But the moment it starts to submerge in the liquid, another force arises here, the upthrust. So, there is an upward force acting on the object that actually, since it is acting upwards, the resultant force keeps decreasing. But since still the resultant force is downwards, so the object will be accelerating downwards. As it starts to move in the fluid, there is a viscous drag that acts on the object. So, this particular viscous drag, however, you can see at the moment the object is released, the speed is still 0. The viscous drag is also 0, but it accelerates due to gravitational force. But as the speed increases, you have studied that the viscous drag increases, causing the net force to decrease, although the acceleration is decreasing. At this point, people would think that actually, okay, the upward force is increasing, acceleration is decreasing, how come the speed is still increasing? Of course, the speed is still increasing, but at a slower rate. It is still accelerating downwards, but at a slower rate. So, when will this stop? When the forces acting on the object are completely balanced. What do you mean by balance? Here there are actually three forces acting on the object. So, one is weight. We normally mark the free body force diagram, weight vertically downwards. And there are two forces upward here. One is upthrust, the other one is viscous drag. So, when we actually say the forces are balanced, at terminal velocity, the downward force is equal to upward force. So, W is equal to U plus F. So, when this condition is satisfied, the object reaches its constant maximum velocity and what we call the terminal velocity. So, how do you define the term terminal velocity? It is actually defined as the constant maximum velocity attained by the object when it is moving through the fluid. The forces acting on it are balanced. And if you are asked to draw the free body force diagram, you can see weight, upthrust plus drag upwards. It is almost of equal length you have to show because they are actually equal in magnitude. But at this point, you would be getting a question on draw a graph of velocity against time and mark the terminal velocity. The typical shape of this graph is always like this. You can see it keeps on increasing and it reaches a constant, or what we call it a steady speed. This steady constant maximum speed only we call it as terminal velocity. And this graph is very important for your exam. So, to drift downwards at a constant velocity, the upthrust plus the drag must be equal to weight. Now, let us see how to derive an expression of terminal velocity using Stokes' law and Archimedes' principle. So, this derivation anyway all of you would have studied, but a simple concept what I have to highlight here is, this is the equation you can start with in order to derive this particular complicated formula. You can see the formula appears to be a little bit complicated, but a simple start is, if you know this equation at terminal velocity, this is what happens. So you can easily write what is weight of an object. It is the density of the object, that is mass into acceleration due to gravity or gravitational field strength. And upthrust is, today we learned this actually, it is the weight of the fluid displaced. So you will be getting a formula like this. Whereas the viscous drag is given from Stokes' law. So you will be getting the maximum viscous drag when the object reaches terminal velocity. If you could substitute each of these expressions in a very simple way in this equation and make the terminal velocity as a subject, so you can see from here it's very clear how it is done. You will be arriving at a formula of terminal velocity 2r square g into rho s minus rho f divided by 9 eta. So this equation clearly shows that the terminal velocity depends on the difference in the density of the object and the fluid, the radius of the object, and the coefficient of viscosity of the fluid. So for the given fluid, how does the terminal velocity changes with the size of the object? You can see actually the terminal velocity is directly proportional to r square. More the radius, more will be the terminal velocity. The possible question here is, if we are taking identical material but different size objects, a smaller sphere and a larger sphere, both are dropped in the fluid of the same viscosity. People would think that the material is different, same, so you will be getting the same terminal velocity, but it's not so. The terminal velocity here actually depends on the square of the radius. So more the radius, that means the larger sphere will attain more terminal velocity than the smaller sphere. So if the radius is doubled, the terminal velocity becomes 4 times because there is a square term. So you need to be very careful when answering questions related to the radius of the sphere and how does it affect the terminal velocity. So anyway, you have seen this graph already. So let's move on to the last section of our fluid dynamics, that is types of fluid flow. But in Stokes' law, I just mentioned the 2 conditions. One is it's valid for small spherical object. The second condition is the fluid flow must be laminar flow. What is this laminar flow and what is this turbulent flow that you can see here? Laminar flow, turbulent flow. What is this fluid flow? Actually, this fluid flow is explained based on the lines of flow of the fluid particle. Each and every fluid particle will be moving at certain velocity. If along a line of flow, all the fluid particles are at same velocity, the lines of flow do not cross each other. You will be getting a perfect parallel lines of flow. That is what we call, you can see from here very clearly, laminar flow. Whereas if the velocity keeps changing, what happens here is, you can see the lines of flow crosses each other, causing the turbulence. So whenever there is turbulent effect, it disturbs the motion of the object. If you think of a practical situation, an aircraft, you would have heard about this terminology, turbulent effect, turbulence. So whenever it encounters turbulence, the object is disturbed or the motion of the object is disturbed. So you should know clearly the cause of that disturbance. So how exactly the body of the aircraft is designed so that the turbulent effect is completely, or we can say, minimized to a smaller extent. Before moving on to that particular section, let us see, it's a very important question here, the differences between laminar flow and turbulent flow. As I said, at least you should notice it, 3 differences, but most of the questions they are asking only 2 differences. But for your information, it's better to know all these points. So in the case of laminar flow, at any given point, the velocity is constant. Whereas in turbulent flow, velocity at any given instant varies with the time. So here, since the velocity is constant, the lines of flow do not cross each other. Whereas in the case of turbulent flow, since the velocity is changing, what happens means it crosses and it causes turbulent effect. The best example for laminar flow or the smooth flow is a slow water flow along a smooth pipe. But air flow in a storm could be a best example for turbulence. But the body of the aircraft is streamlined in such a way that this turbulent effect is minimized. You could see this is actually a practical application, how the body of the aircraft is designed so that the turbulent effect is completely minimized. You can see from here, this is a laminar flow, but even if the object is moving, the body of the aircraft is streamlined in such a way that it will not cause the velocity of this fluid particles to change. So it would once again go with the streamline motion, or we can say laminar flow, unless it is affected by some external disturbance. So the fluid dynamics plays an important application in the case of all these practical examples. So in addition to this, you will be getting actually many numerical questions also related to fluid dynamics. One of the important calculations is calculate the upthrust. Here I want to insist one important point. We are asked to show that upthrust is equal to some value. For example, show that upthrust is equal to 15 Newton and the data of rho, V, and anyway of course G will not be given in the question, but it is there in the formula sheet. So rho is given, V is given, G of course you know it is 9.81 Newton per kilogram. So you would choose the correct formula, upthrust is equal to rho, V and G. You will be putting the substitution, and always the students have the tendency, already the answer is there in the question paper. So you have the tendency to write the answer as it is after substitution. But please don't do that, because in A-level physics exam, if any show that question comes, the final answer has to be with one more significant figure than the stated value. So if it is given as 15 Newton, for example, your calculated value is 14.8, leave the answer like that, then you can say it is about 15 Newton. For this particular step only, you are getting the last mark. If you are ignoring this, you are losing that particular mark. So always keep in mind when you are answering numerical questions, it has to be, your calculated value has to be given in 3 significant figures. And the final answer, it is about, but at this point, another doubt arises with the students, that is, for the preceding questions, should we use the stated value or the calculated value? If you are sure of your calculated value, of course, you can go ahead with the calculated value, but it's always safe to use the given stated value. So there would be anyway other questions, some sample questions you would have already done it, but and all these things actually, if you have any queries on this, you can direct to us and we will be explaining all these questions in panel discussion session. Okay. Hope you would have actually got benefited from today's session. So I am winding up today's session here. Practice before you go for the exam. Anyway, wish you all the best.